This is lecture 22 where we'll be looking at how we can solve hyperbolic partial differential equation using the finite difference method. What I want to point out here before I start the lecture is that the hyperbolic PDE that we are going to look at is actually first order instead of the second order that we have gone through in parabolic PDE. So if you recall from what I've mentioned in class, a second order hyperbolic PDE is your wave equation. In this lecture, we'll be looking at what we call the advection equation, and the advection equation has this form over here. Okay, now although this is first order, the solution that we get or the analysis that we do with finite difference method on the advection equation is actually very similar to the wave equation for second order PDE, and that is why for simplicity we are going to be looking at the analysis of a hyperbolic PDE based on the advection equation. So in this advection equation, you have temperature as your unknown, u here is your velocity, and in your partial derivatives you have d temperature d time plus u times dt dx is equals to 0. So some of the examples where the advection equation applies is the advection of heat. For example, you have flow at a certain velocity and the flow is carrying heat, so the change in the heat would actually cause the change in the temperature, which can be described by the advection equation. So you're going to first solve this by the FTCS scheme. So if you recall from lecture 21, FTCS basically means that FT your forward time and CS your central space. So in your forward time, your d temperature by d time would be given by Tj of n plus 1 minus Tj of n divided by delta t. Okay, and this would have an order of accuracy of delta t. So this is your forward time scheme. In your central space scheme, right now instead of d squared t dx squared, we have dt dx. So we have to use the central difference scheme to approximate the first order derivative of dt dx, which will be given by Tj plus 1n minus Tj minus 1n over 2 delta x. So this would have an order of accuracy of delta x squared. So right now, if you substitute these partial derivatives into your advection equation, you'll end up with, on your left hand side, Tj n plus 1 minus Tj n divided by delta t plus the velocity times the central scheme divided by 2 delta x is equals to 0. So as in the parabolic PDE, when we do this, we are going to rearrange it such that all the unknowns are on the left hand side and all the known values are on the right hand side. And if you look at this, the unknown values that we have are actually given by temperature at the next time step, because we assume that everything at time level n is known to us. So if you rearrange this, you will get Tj at n plus 1 is equals to Tj n minus u delta t 2 delta x, and this you will get the j plus 1 and the j minus 1 at time level n. Okay, so this entire equation here is referred to as the FTCS scheme for the wave advection equation. And if you look at this, and if you're going to solve this, this would again be your axis x. You have your 3 points at j, j minus 1 and j plus 1. So if this is time level n, you will be solving for time level n plus 1 here. Okay, and in order for you to find the solution at point j at the next time level, which is this point right here, you will need contribution from this point, and this point, very similar to your parabolic PDE scheme. Now, suppose that you want to solve a simple example. Let's say you have d temperature d time plus 0.5 of dt dx, and the solution domain is valid from minus 10 to 10, and you're given the initial condition of this. So forget first about the boundary condition. If you're going to solve this, you need boundary condition as well. But I'm just showing you this example to illustrate how we can actually apply this FTCS scheme. So just for simplicity, let's say for our domain here, we discretize it into 2 segments. So if your domain is valid from 10 to minus 10 to 10, this would be your delta x, and this would be your delta x, meaning that the middle point here is 0. Okay, so if you recall from your FTCS scheme, you have Tj at n plus 1 is equals to Tj at n minus u. So u here is right now 0.5. So 0.5 delta t over 2 delta x Tj plus 1 minus Tj minus 1 at time level n. Okay, so the first thing that we do is we have to use this initial condition here to calculate the initial values for the 3 points that we have. So we just set j equals to 0, j equals to 1, and j equals to 2. So this corresponds to j0, this corresponds to j equals to 1, this is j equals to 2. So if you substitute in the values of x here, you're going to get all these 3 values. Okay, so there's only one point that we are going to find out, because the other 2 points will be known from your boundary condition. So right now, if I set j is equals to 1 and n is equals to 0, I will get t1 at time level 1 is equals to t1 at time level 0 minus 0.5, and just for simplicity, let's say delta t is equals to 1. So you have 0.5 times 1 over 2 times delta x would be equals to 10 here, and this would be t at j plus 1, which is your t2 here. So this would be 0.0027 minus tj minus 1, which is this value. So if you calculate this, you get your value of temperature at the middle point at the next time step of delta T. So of course, this is just an example to illustrate. If you're going to really solve this accurately, you need to use more points in the spatial discretization, as well as more more levels in the time discretization. Now, that would be the theoretical thing that you have to do. If you actually write a numerical code or MATLAB code that just solve this with smaller and smaller delta T and delta X, you'll get a solution like this, where this is your x-axis and this is your time axis. So advection equations are basically propagation of wave, which can be thermal wave, acoustic waves, or so on. Okay, whatever that is being advected by the velocity here. So if you look at this equation, you can see that you get oscillations that happens like this. Okay, so if you're going in this direction in time, you can see that if this is actually the thermal wave that you're looking at, it doesn't propagate as a single wave. Instead, there are oscillations like this. Now, is this the actual solution that you're supposed to get? I can tell you that this is actually not the actual solution, because you're supposed to get one single wave that is propagating with time. What you have here is actually instability. Okay, and the reason for this instability, you can find it out by using the von Neumann stability analysis that we have done in the that I've shown to you in the previous lecture. So in the next part of this lecture, I'm going to go through the von Neumann stability analysis for the advection equation.